brain is made of maybe thousands of different kinds of cells called neurons that are built into very dense intermeshed networks that communicate. Each of these neurons computes using electricity. This cycle implements behavior and thought and emotion, all these different kinds of things. We also think that deficits in these electrical computations underlie many brain disorders that affect over 1 billion people around the world. In optogenetics, what we're doing is we're putting molecules that convert light into electricity into neurons, the cells of the brain. Then when we shine light on those neurons, light gets converted to electricity and allows us to turn on or off those cells. The goal here is to find a way to control the electrical activity in some cells and not others in the network. To do that, we had to turn to the natural world. It turns out that throughout all the kingdoms of life, in plants and funguses and bacteria and so on, you can find photosynthetic or photosensory molecules that convert light into electricity. So we borrowed these molecules from nature, and then using tricks from the field of gene therapy, we can put them into neurons. Now, these molecules can convert light to electricity, and they do it just in the neurons that we want to control, and not all their neighbors. So we can deliver these molecules to some cells and not others, and then when we shine light on that network, we can turn on or off that subset of the cells. If we can turn on or off a set of cells that's embedded within this dense matrix, we can figure out how do they contribute to a behavior. For example, if we can turn on a set of cells, we can figure out what kinds of behaviors can it initiate. If we can turn off a set of cells, then we can delete it momentarily and figure out what it's necessary for. So by being able to dial in information into cells in the brain and to delete them, we can try to figure out how they contribute to networks and the behaviors and diseases that arise from brain computations. We can hunt down the exact set of cells that are contributing to a specific disease state, or which, when activated or shut down, will remedy that disease state. That's really important because right now a lot of drugs are developed that target molecules. But molecules are found throughout the brain, and in fact many cells in the brain might be very molecularly similar to one another. If we can target circuits in the brain, though, we might be able to develop much more specific drugs. Imagine if we could hunt down the exact set of cells in the brain that, when activated, remedy a brain disorder, and then we can go in and look at the exact molecules in those cells. Maybe we can find drug targets that are much more specific than existing ones. You might also imagine that we could use optogenetics to directly control brain circuits in patients with brain disorders. Electricity is used to stimulate the brain in deep brain stimulation. If instead we could actually aim light at certain cells and turn them on or off, we might be much more specific. Rather than using electricity to turn on and off the cells of the brain and have many kinds of cells activated, the ones we want to affect as well as all their neighbors, if we could make just one disease-associated subset associated with light and we can turn them on or off, we might be able to treat them with much more specificity. So far, optogenetics has had a lot of impact in the scientific world, but it hasn't been used in any human patients yet. There are a couple reasons why. One is that it requires a gene therapy to deliver the gene that encodes for these light-activated molecules into the body. Currently in the US, there are no FDA-approved gene therapies. In Europe, there's just one. Another issue is that these molecules come from organisms like algae and bacteria. And so if we are putting these molecules into the body, would they be detected as foreign agents and attacked by the immune system, for example? What we need is a paradigm shift in how we think about treating brain disorders. And one of our major stances is that we need new technologies if we really want to either understand the principles of treating brain disorders, hunting down the exact cells in the brain that can help us treat brain disorders, or to develop new modalities, new forms of energy, new strategies for treating brain disorders by correcting the computations within the brain.